Good morning, good afternoon. Welcome everyone to the webinar on solar-powered water systems in humanitarian context towards more sustainable and efficient SPWS. My name is Ranisha Basnet and I'm working at Energypedia and will be your moderator for this webinar. Today I'm also joined in by my colleague Asinath Kiprono from Oxfam, who will be assisting with me with the Q&A round. As you know, this webinar is organized jointly by the Solar Hub, IOM UN Migration, Oxfam, USAID, and Energypedia, and is part of an ongoing webinar series, which is a 4-part webinar series. We kicked off in November 2020 where we had our first webinar on what is SPWS, solar-powered pump water systems, talking about the different configurations. Then in Jan 2021, we dived deeper and talked about how can we retrofit existing water schemes into solar-powered schemes. And then in March 2021, we talked about specific considerations and limitations. And today we are diving even further and talking about how to make solar-powered water systems more sustainable and efficient. If you have not joined us for the earlier webinar, my colleague has dropped the link to our past webinar in the chat box. So please have a look at it where we have recorded the presentations as well as the recording from the earlier webinars. So you can have a look at them. And not only the webinar materials, we have also added all the links to external publications and other resources that are useful for you to understand the topic in depth. So moving forward, let's have a few house rules for today. For this webinar, we are accepting all of your questions. So on your screen, if you are using a laptop, you should see on the right side of the screen a control panel where you have a box called questions. There you can type in your questions and send it to us, and my colleague will be accepting all the questions, which we will later pass it to the respective speaker at the end during the Q&A round. So do tell me to whom the question is addressed to. Since we have 4 speakers today, so you can either write speaker 1 or organization's name so that it is easy for us to sort them out and pass them to the respective panelist. If you are using a tablet or a phone, you might not see the same control panel that I show you that is shown in my screen right now, but rather like a banner on the top of your screen, and there is a question mark. So if you click on that question mark, then you should have a pop-up where you can type in your questions. So please do send in all of your questions during the Q&A, during the entire webinar, and we'll address them during the Q&A round. So let's have a quick look at today's agenda. Today, as I said, we have 3 organizers who are presenting on different topics. We will kickstart with the presentation from University Politécnica de Valencia about how to increase efficiency of solar water pumping schemes. Then we will go into a case study from IOM and also talk about how to operate and maintain the systems. And finally, a presentation from Eternal Sun on how to choose good quality solar components. So without further ado, let's dive deeper, and I would like to welcome our first presenter for today, Dr. Salvador Segue. Dr. Salvador Segue is a professor at the Polytechnic University of Valencia since 1991 and has extensive experience in the field of solar-powered water schemes. So Professor Salve, I'm going to send you a request to share your screen. And in the meantime, you can already unmute yourself. So I've sent you a request which should pop up on your screen. Yes, we can see your screen. If you could, yeah, perfect.
Okay, I think that it's all okay. You can hear me and see my presentation.
Yes, please go ahead.
Okay, can I start?
Yes, Professor, please.
Many thanks. Well, good morning for all of you. My name is Salvador Segui, and my presentation is going to deal with the topic increasing efficiency of solar water pumping schemes. I'm a member of the university, and my research and development group started the work in PV systems before 2000, including training courses in PV system as part of our common activities, moving to online training in 2010. I have included some photos of the different PV installations that we manage in the university, starting in 2000 with a PV grid connected installation with 70.5 kilowatts, this one, that was connected to the power network of the university, being one of the first examples of self-consumption in Spain. On the right bottom corner, here, we can see one installation in which we develop practical courses in PV systems, including several technologies of PV modules and inverters. We have several courses in Spanish, and also we have 2 online courses in English. Here you can see the contact information for these courses. You can find more information about the topic that I'm going to develop during the session in the ebook that you can see here. Sorry. After this short introduction, you can see the different parts in which I have divided my presentation. We are going to start revising the factors influencing solar energy production. We are going to revise to estimate the typical losses, seeing the typical values related with the different factors, dividing them in 3 groups: losses related with the PV modules, with the temperature, or with the balance of the system, that include the rest of components of the installation apart from the PV modules. Finally, I will give you values for the energy losses and efficiencies in a solar water pumping facility that we have mounted in my university. The block diagram that I have included in the slide shows the components that you will find in a medium-large power solar water pumping facility. The DC electrical energy produced by the PV field is converted by the power converter unit in a 3-phase system in the output with variable voltage and frequency in order to control the flow of power to the motor pump group that is here. In this way, the power converter unit can balance the energy generation and the energy consumption in the system. The energy generated by a PV systems can be calculated with this expression that we have here, where the different terms are explained below. The first term is the peak power of the PV field. The term peaks in hours represents the energy reaching the PV field and depends on tilt, orientation, or other specific conditions of the location where the PV system is mounted. The performance ratio that we can see here includes the loss factors in the PV installation, and its calculation is done with this other expression, in which we multiply the terms corresponding to the loss factors that we can identify in a PV installation: tilt, temperature, orientation, shading, dirtiness, mismatching, and others that we will see in the following pages. The last term in the expression is related to the period in which we want to estimate the energy generated by the system. This expression can be adapted to estimate the hydraulic energy that the system can produce if the corresponding performance ratio is obtained or is used. The reduction of the losses equivalent to an increase in the performance ratio yields to an increment of the energy generated by the system, so a greater volume of water can be pumped in this case. This table that appears in this electronic book shows the most common values used for the loss factors that can be identified in PV systems. Temperature and wiring will be explained in next slides. The tolerance can be included as a loss factor because some manufacturers work with negative tolerances, +5 and -5, for example. And sometimes it happens that all the modules in our installation have a peak power corresponding to the negative part of the tolerance. So the result is that we have less peak power than the nominal or rated power that we expected. Nowadays, the most important manufacturers offers modules free of light-induced degradation or potential induced degradation. About soiling and the frequency of cleaning depend mainly of the specific conditions of each installation. Typical values considered are in the range of 2% to 5%, but installations near of dusty roads or industry can reach values greater than 50%, as you can see here, and will need a frequent cleaning of the PV surface. Although some power converters nowadays can operate with maximum efficiencies close to 99%, the loss factor can be greater than the 5% that we are including here, due to the point of operation is changing during the day. So in very few cases, it operates around the maximum of efficiency of the power converter. Here, we include some of the loss factors related with the PV modules in this list. In the images, you can see different PV technologies, the small strips of overlapping cells inside the module, or cells with multiple bus bars, or half cells, as we can see here. Mismatching losses, this one, appears when modules with different characteristics are connected in series in a string. The current voltage curve that I'm including here was obtained with a curve tracer in one of our installations, including 3 different types of modules, as we can see by the 3 different levels or steps in the short circuit current. Here we have the short circuit current, and we can see how it changes from using the values measured, that is the green line. The first value corresponds to 5.4 amps. Then we can see a decrease to a level that is around 5.2. And finally, we can see that the short circuit current is in the scale of 4.8 amps. So we can see that with the same size of the PV cells, 5 inches, the peak power of the modules in the test were 87 watts for this current, 85 for this other, and 70 watts in the last case. So this is a representation of the mismatching losses in the PV systems. Common values used for crystalline modules for de-aging are around 0.4% per year, with maximum values that can arrive until 0.8% per year. Module mounting conditions have an important effect in the PV cell temperature, depending how the air can flow through the backside of the modules. Also, distance between rows of modules has an important effect in the losses due to the inter-row shading. The following plot shows how is the variation of the PV cell efficiency along a sunny day. Here is the efficiency of the cell. We can see how the PV power, this line, is proportional to the irradiance, and how the PV cell efficiency varies along the day. It can be observed a small decrease in the PV cell efficiency at midday, this part, when the cell temperature is in its maximum values. We can compare the efficiency of the module in standard test conditions with the maximum values obtained in this day that arise to 12%. The equations included in the slide permit to estimate the losses due to the temperature. Here are the calculation of the losses and the effect in the performance ratio. The normal operating cell temperature, this factor, and the temperature coefficient of the power, here, varies attending to the PV technology, as you can see here in the values included in the table. The normal operating cell temperature varies between 41 to 49 values, maximum values that you can find, degrees Celsius, and the temperature coefficient of the power is negative. We lose power if the cell temperature increases, with values varying between 0.3 to near to 0.4. Respect to other losses in the PV system components listed in the table, we can see in the graphic the losses in the different conversions in a PV water pumping systems. The difference between the PV power and the output power in the variable speed drive, this difference between the powers, corresponds to the losses in the power converter unit. The difference between the variable speed drive, the green signal, and the hydraulic power, this one, corresponds to the losses in the motor pump group. Here, all this difference between the powers. We can see how the PV power is quite proportional to the irradiance, but at the beginning of the day and at the end of the day, there is irradiance, but there is no PV power. These losses are related to the minimum irradiance needed to start or maintain the operation of the water pumping system, usually denoted as the threshold irradiance. The next slide shows the clipping losses due to the oversizing of the PV field with respect to the power demanded by the water pumping systems. The clipping can be seen here in these 2 days. Typical oversizing factors are between 1.4 and 1.9. In our case, the oversizing factor is 1.46. And in summer, it's possible to find the clipping of the power, this flat plane, in sunny days with good levels of irradiance, just like we are seeing here. High oversizing factors result in an increase of the pump volume and in a decrease of the performance rate of the installation. About wiring losses in cables, usually are in the range of 1% to 3%, but can be greater when the distance to cover are large. The general recommendation is to work with oversized cross sections in the wires respect to the values obtained during the design of the installation. This slide shows the components used in our photovoltaic water pumping facility. We have 8 modules in series, obtaining a peak power equal to 2.4 kilowatts. The variable speed drive has a rated power of 2.2 kilowatts and includes a maximum power point tracking algorithm to operate the PV field in the best operating conditions. The distance between the PV field and the variable speed drive is around 180 meters. And we have mounted cables with 16 square millimeters of cross section in order to maintain the voltage drop in acceptable values. The 1.5 kilowatts pump is mounted in a tank in a lab of the building, and the water flows until another tank mounted in the roof of the building with a static head of 15 meters. We have been seeing previously the values of the powers in the different parts of the installations. And the new plot that I have included here shows the efficiencies and the flow rate of our system. Efficiency in the variable speed drive, the one blue, is calculated dividing the power in the output of the power converter by the input power that corresponds to the PV power. The efficiency in the motor pump group is calculated using the hydraulic power divided by the power generated by the power converter unit, the variable speed drive. The total efficiency is obtained, this one in red, considering the hydraulic power divided by the PV power, the one obtained here. As is shown in the plots, efficiencies are varying along the day due to the variations in the irradiance. Due to that, in the next slide, we analyze the operation of the system using energies and performance ratios. The block diagram includes the powers and efficiencies calculated in the facility. We can see radians and powers in the different parts and efficiencies in the different parts of the installation. In the list here, I have included the energies obtained during a day with 5 peak sun hours. These energies that we have calculated permit to obtain the performance ratio of the facility. The performance ratio of the photovoltaic water pumping system considers the peak power of the installation and the peak sun hours, energy received by the PV field, obtaining a value that is around 25%. This is just the expression that we are evaluating for this calculation. In summary, it should be remembered that there are some losses that cannot be avoided, like temperature, aging, or converter efficiency. Other losses can be minimized, just like wiring, shadows, and dirtiness, and others that are sometimes not included in the estimations, but are very important during the lifetime of an installation, just like aging and tolerances in the PV power of the modules. Also remember that improvements of the performance ratio can be obtained using a greater cross-section in the cables, or using high-quality modules, or planning more cleanings of the PV fields, as we have detailed here. That concludes my presentation. I hope it has been useful to all of you. Many thanks for your attention.
Thank you so much, Professor. I'll quickly switch back to my screen. So first of all, thank you so much for sharing all the factors about that that influence the efficiency of the solar water pumping schemes. And like Professor mentioned, we will share with you the presentation so that you can have a look at it at your own time. And also the book that he mentioned, we will share the link with that. So stay tuned for the email that will go out after the webinar. And now let's have a quick poll. This poll is to get to know you, the audience, better. So I'm going to drop a poll question on your screen, and it should be popping up on your screen. And do use the poll question. Tell us where are you based today? So where are you logging today from? Are you in Asia, Africa, Europe, Latin America, or the Caribbean? So I can see the voting is ongoing. So we will leave the poll questions for another 10 to 20 seconds. And these questions are to understand you, the audience, better so that our future webinars are more catered to your time zone, to your needs, and so on. So as the poll questions are still coming in, let's leave it for another 5 seconds. And now I'll close the poll and display the results. So as you can see on your screen, we have a lot of our audience who are tuning in today from Asia, followed by Africa, Europe, others. So welcome to all of you one more time. And now I have a second poll question popping up on your screen. So do tell us, in which sector do you work? Are you working in humanitarian, development, both humanitarian and development, academia, and so on? So we will leave the poll question for another 10 to 20 seconds. The answers are popping in, so let's leave it for another 10 to 15 seconds. And now slowly I'll close the poll. So if you haven't voted, so please vote now. And now I'll close the poll and display the results. So the results are shown up in your screen. So a huge chunk of our audience today are working in the humanitarian organization, followed by humanitarian and development, followed by both development and academia, and others, of course. So thank you so much. And now moving back to our presentation, I'm happy to invite our second presenter for today, two of our colleagues from IOM. So our first colleague is Alberto Larry from IOM. Alberto is a wash and energy manager with IOM and has over 15 years of experience in the relief sector. And he's joined today by his colleague Alessandro Petrone, who is also working for IOM, especially IOM's Cox Bazar since 2017 as program manager, and has over 19 years of experience. So Alberto, Alessandro, the floor is yours. Alberto, I'm going to send you a request to share your screen. And in the meantime, please unmute yourself. So Alberto, if you could unmute yourself and accept my screen.
Yes. Hello everyone.
Yes.
Do you see my screen?
Yes, it's loud and clear, and please proceed.
Okay. Thank you, Vanessa, and everyone for being here for this webinar. And I've been working now for 5 years in the clean energy and wash nexus as a project manager for the Global Solar and Water Initiative. And I'm going to talk a little bit about operation and maintenance of solar power water schemes. And this is a vast subject. In this presentation, I'm going to try to quickly show some data from assessments and past field visits, and show some of the best practices that we believe are to be there to ensure O&M in solar systems. But since this is the last webinar of the series, I thought I would start by trying to give some kind of facts and global overview on the use of solar power water systems. In 2019, we managed to map nearly 1,600 water schemes that year were solarized by WOS actors in 42 different countries. We, however, interact through different services of the Global Solar and Water Initiative with WOS agencies in 91 countries, and also through individual interviews with WOS engineers, we came to the conclusion that probably that year there were many more than those 1,600 water schemes that were solarized by WOS actors. For all the countries where we could know number of solarized water schemes at different moments in time, we consistently saw that there was a growth in numbers as year passed by. And specifically for humanitarian emergency settings, the very high rate of solarized water schemes that we can find in places like northeastern Nigeria, Uganda, Yemen, Bangladesh, not only in camp settings, but also at community level, is unseen of before 2015 or 2016. The other issue that we were worried about, and we tried to see how it was going, it was about how these systems are working in those settings. In assessments carried out in Kenya and Zimbabwe, we found functionality rates of solar systems of 92 and 88%, so much higher than other diesel-based technologies or hand pumps. And I'm telling you all this to share our conclusion that the use of solar water pumping systems in the relief sector and beyond is going global, is growing, and that the technology is robust enough when systems are well designed and properly operated and maintained to last for long years. On the other hand, what we have is about 1 billion people on the planet living in off-grid areas, and an additional 1 billion people living in areas with weak or faulty grids. Most of those 2 billion people live in countries that are located within what is called the solar belt. This is an area of the planet that gets a high average of solar irradiation levels. And for those communities in those countries in the solar belt without access to electricity or with access to electricity, and that need, in order to get fresh water, an electrical water pump, solar power water systems offer a unique possibility to ensure less costly and more reliable access to water. In summary, we have in our hands this wonderful technology that has a transformative potential for millions of people. For this apparently expanding use of solar water pumping system to make sense and became a success story, systems need to remain functional over time. It doesn't make sense to install a solar panel that can last for 25 years if the water scheme became faulty after a short while and there is no planning and nothing is done to bring it back to functional. And what we have seen through having trained around 1,000 WASP engineers on solar water pumping in the last years, having received almost 500 queries on this subject and having visited like a dozen of countries, is that while practitioners get very interested and excited about using solar panels, about designing systems, about installing them, there is very little curiosity or attention given to understand the distinctive aspects of operating and maintaining solar pumping water systems. And this is dangerous, and we are working and we are hoping that this will change, and if you are an implementer, that you give a deeper thought of these on these aspects. When thinking about operational maintenance models, what I'm showing there in the slide, 4 distinctive management models that we found in our assessments. This is not an exhaustive list. There are variations and different combinations observed during field visits in different places and countries. And what is important to retain is that, of course, one-size-fits-all approach cannot be adopted for the management of solar power water systems. Different models will work in different settings. What work in one place won't work in another, and vice versa. And because a model is working in one setting doesn't mean that it will work in others. But looking at the table, and for this webinar, perhaps the most interesting models are the last 2. We have the UN NGO implemented and managed model that is very usually found, especially in camp settings, and that when it comes to operational maintenance, normally it's a little bit more straightforward, but I'm going to leave my colleague Alessandro to talk about his experience on this in Bangladesh. And then we have the community-based managed model that is, of course, a little bit more complex. So what is conducive for communities to be able to make solar water pumping last for long? On the left of the slide, you can see the overarching characteristics of successful community-managed solar systems identified in our evaluation in Kenya. And on the right, you can see the key attributes of successful O&M models with basically 3 components: financial sustainability, technical support, and dedicated personnel. And as you see, if we think of O&M for other pumping technologies, nothing is really very different at this stage, but there are within these 3 components and details that are distinctive for solar. If we look at financial sustainability, we think that we as a WASP sector need to better understand and have a more clear vision on the cost involved in operating and maintaining a solar system, and then discuss this with communities in charge or the owners of the systems in order to have a viable plan for the long term. We still find those teams, those engineers, those organizations that convey the message that water is for free to communities, just because the sun is free and there are no associated costs to the operation of the system. And in this regard, again, there needs to be a shift in that narrative to communities, from tapping into a cost-free source of energy for water pumping to accumulating funds for future system replacements. Yeah, NGOs, agencies, and communities need to understand that while there are minimal recurrent day-to-day costs to operate a solar system, there might be significant one-off costs required to ensure continued long-term operation, whether this is linked to replacement of an inverter or having a technician coming from the capital to have a look to the system. Consequently, at community level, water should be, we think, provided at a fee to ensure funds for repairs, maintenance, and replacement of parts. I'm showing there a graph from our Kenyan assessment, showing that 69% of communities were paying for water, the ones relying on solar standalone system. But please take this as top of the class. We have also other partial assessment in other 4 countries showing that the numbers are much lower. The other aspect that is distinctive for solar systems managed by communities is the difficulties for communities to save money over time when there are no recurring costs associated to operation. So collecting fees that go into into a box, into a bank, and that are waiting there for months and years for a problem to be, so that you have funds to respond to it, is a very difficult, is a very hard thing to do for many communities. And in this regard, planning for the good use of these funds and establishing this dialogue with communities to ensure accountability of those funds is going to be more critical than ever. In terms of dedicated personnel within the community for the operation and routine maintenance, understanding routine maintenance as a set of simple activities that, when they are performed, result in a good, let's say, performing system on a daily basis, and that consists of a set of simple actions that I'm showing there. Things like cleaning the panels, collecting the water fees, keeping records. These activities, this operational routine maintenance, has been proved over time that can perfectly be managed by community members. That, however, need to be trained for this. And I'm sharing there 2 separate countries, assessment in 2 separate countries, in where we found that 77% and 90% of the NGOs involved in the installation of solar systems were doing so. We're incorporating training for communities for them to become aware and knowledgeable about how to operate and how to do the routine maintenance. And you may think that this is high. My thinking goes to those 23% of communities that perhaps are struggling as we speak, having a very reduced yield of water because nobody told them they need to clean the panels every week. Yeah. So this is something that should be compulsory, that most of the organizations involved in installation are aware of, but that should be always there as part of our program. In terms, finally, of technical support, understanding technical support about having access to knowledgeable technicians that can conduct troubleshooting or repairs when needed. It is completely unrealistic to think that by training communities, they will be able to repair or troubleshoot the system whenever it is needed. And operation and maintenance plans that are based in this idea will very likely fail. Communities are trained for operation, communities are trained for routine maintenance, but for repairs or troubleshooting, specialized knowledge is required, and there will be the need to get support from knowledgeable technicians, whether it is from the private sector, the government water office, your organization, or others. 77% of the NGOs that we surveyed delegate design and installation to private sector companies. And we found that when that happened, very little thinking is given to long-term maintenance. Private sector companies are interested in selling components, are interested in doing installation, that's their business. Most of the times, they are not the ones that are going to bring the issue of long-term maintenance on the table. Most of the times, communities won't bring that issue either. So if you don't take care of it, if you don't become aware of how it's going to be, what it could be, planned and discuss this with the communities that own the systems, these things are not going to happen. For places where you don't have all the conducive and right conditions for these things to happen, especially places where technicians are few or only present at capital level, after-sale maintenance agreements are considered best practice to ensure timely technical support. But we have to say that so far these are quite rare to find. We found only 15% of NGOs surveyed are having this in mind in the places where they are working. These long-term thinking of maintenance aspects are generally a big gap when it comes to community-managed solar systems, and we think this is where we have to pay a little bit more attention, because if not, what we will find is that thousands of solar systems that are became non-functional in 8 or 10 years because there is no thinking on this. I'm running out of my time, and I'm going to leave you there some takeaway messages, trying to summarize what I have said. And I hope I didn't sound too negative or pessimistic when talking about O&M. These are always difficult issues. We do believe that solar power water supply technology for camps and communities in rural or urban settings is technologically more than ready for being mainstream in a vast number of contexts and countries. And however, to ensure the sustainability of the systems, we need to take into account in our programs, in our projects, the considerations outlined in this presentation and address them. I'm going to leave my contact there. If you have any comment, any question, or you have any evaluation in your country from your organization involving solar systems, I will be more than glad to hear from you. And you can find our assessments and other material related to solar pumping in that webpage. So that's all from my side. Thank you very much for your attention, and back to you, Anissa.
Thank you, Alberto. Then we will quickly switch to Alessandro as we are running out of time. So Alessandro, I'm making you a presenter, and please unmute yourself and you can begin your part.
Thank you, Anisha.
Yes.
Yeah. Good afternoon, everyone. So I will try to be quick and straight to the point because of time limitation. My name is Alessandro Petrone, and I am the head of WASH for the IOM in Cox's Bazar, Bangladesh. I'm going to present to you the operation and maintenance requirements for a large solar scheme. It's the solar water supply system that we installed in Camp 12. This camp is one of the camps hosting the Rohingya refugees in Cox's Bazar in Bangladesh. First, I'm going to give you a very quick overview of the humanitarian context in Cox's Bazar. Currently, we have 34 camps in Cox's Bazar district, hosting around 855,000 refugees. Significant influxes have occurred in the past, but the largest one took place in August 2017, when over 700,000 Rohingya refugees fled across the border into Bangladesh. In the northern part of the map, you can see the Kutupalong expansion site, often called the mega camp, where since 2017, over 685,000 refugees are living. And farther south down the Cox's Bazar Peninsula, there are around 170,000 refugees living in other 11 camps. My presentation is not moving.
Could you try clicking on the next one? Is it?
I'm clicking, but I mean from the okay. Yes. Okay. In this slide, we can see the operational presence of the WASH partners responding to this crisis. In total, there are around 40 WASH active partners, and IOM Bangladesh hosts one of the IOM's largest WASH programs. We provide assistance to around 300,000 beneficiaries. The IOM WASH unit is currently the area focal agency for 12 Rohingya camps. Before talking about the main topic of this presentation, the operation and maintenance, I will describe quickly the solar-powered scheme in Camp 12. The system has been commissioned in July 2019, and it's the largest water network in the so-called mega camp. Actually, this makes it the largest solar water supply system in the largest refugee camp in the world. It could be the largest system in all the humanitarian sectors worldwide, but till now we haven't verified this. The project is the result of a collaboration between the Japan International Cooperation Agency, the Bangladesh Department of Public Health Engineering, and the IOM. It supplies safe water to around 30,000 people living in Camp 12 and 19 in the mega camp. The design of the system was guided by the following key considerations. One is the capacity of the solar system to provide around 600 cubic meters per day to ensure 20 liters per person per day. The second consideration is to provide a community tap stand within 100 meters for all beneficiary households. The next one is to install enough taps to ensure a ratio of 125 people per tap. It's half of the CR standard, 250 people per tap. The fourth one is to supply water to 53 communal facilities, including health posts, child-friendly spaces, schools, learning centers. And the last one was to install enough water storage capacity to cover the needs of the population during 24 hours and to ensure supply in case of emergency. Talking about emergency, a quick digression. You probably heard about the fire that destroyed the whole Camp 9 1 month ago. This solar water system was the first source of water during the first phase of this emergency. We organized water tracking from Camp 12 from our system to distribute clean water to Camp 9 and to ensure the life-saving response. In order to maintain the regular water distribution in Camp 12, we were pumping with generator during the night to fill the water tanks. This example shows the advantage of having an hybrid water scheme, but at the same time, to rely only on solar to reach the standard daily water demand. The slide here is showing the water pipeline network and specifications. The network is covering a total area of 0.88 square kilometers through almost 10 kilometers of different size of pipes. And a total of 358 taps were installed for the community, so that the ratio of 106 persons per tap is achieved. We have in the system 187 panels, each 330 watts. Total power of the system is 61 kilowatts. It was designed to produce a maximum yield of 60 cubic meters per hour from 9 a.m. to 4 p.m., even in case of low sun irradiation. It works with a backup 33 kilowatt amperes generator used only for contingency, and it powers a Lorentz submersible pump of 30 kilowatts. The system is producing a daily average energy of 135 kilowatt hours, with a maximum in the month of February and a minimum in July during the rainy season. The solar system alone allows a daily output of around 500 cubic meters of water, equivalent to almost 90% of water demand. The system could provide, indeed, the targeted 587 cubic meters per day, but a limit of 60 cubic meters per hour was set following recommendations contained in the pumping test report. According to field observation, this supply of water is enough for the need of the population. The people, they are eventually complementing it with existing water points that are equipped with the manual pumps. Before the solar powered water system is put in use, it's important, as Alberto was mentioning before, to plan a proper handover with the contractor who installed and commissioned the system. In 2019, in our case, the handover included the system performance testing and monitoring for 3 days to verify the expected values, and also the training of IOM staff and the user's manual with operational and maintenance procedures, as well as troubleshooting corrective actions. We defined also clear terms in the agreement with the contractor for preventive maintenance. Alberto again was mentioning this. These terms are including the maintenance schedule for solar photovoltaic system, 2 years warranty for the system, and 5 years for pump, motor, and controller, and spare parts for key elements, solar panels, submersible pump, inverter. The anticipated work in the handover and the preventive maintenance are helping to minimize the maintenance requirements. The team in charge of the operation and maintenance is made up of 10 Rohingya volunteers from the community living in the camps and supervised by 1 IOM staff. The main responsibilities of this team are to carry out regular jar tests and to prepare the chlorine solution for the inline disinfection system, and also to test the free residual chlorine on daily basis at the tap stands. The team is as well in charge to repair and maintain the network, including the taps, the pipes, the storage tanks, and all the different components of the system. The reservoir site is composed, in our case, by 6 T95 Oxfam tanks. The team of volunteers is responsible to clean 1 tank per week, so each tank will be cleaned every 6 weeks. An important element was mentioned in the previous presentation, the cleaning of the solar panels. During the dry season, it's also important to clean them regularly, at least in our case 2 times per week, to remove the dust and to maximize the irradiation and water production. One additional activity conducted by the volunteers is the measurement of both the static and dynamic water level on a daily basis. This activity is for us essential to monitor the groundwater level, to ensure the sustainability of what we are doing, and to support the regional monitoring program. In this slide, you can see the static water level in green and the dynamic water level in yellow, measured between August 2019 and January 2021. We can observe a decline of water over the last year and a half. This decline is current with the groundwater model developed by us in collaboration with Dhaka University and Groundwater Relief, and it's caused by the concentrations of groundwater abstractions within the megacamp. This is not directly linked to our system, and it will not affect our solar water system, but it shows indeed how water level monitoring is important. This slide is describing an important element of our analysis. It's showing the complete life cycle cost analysis for this solar water system. In blue, you can see the capital investment and operational costs of a system fully powered by diesel generator, considering 8 hours of pumping per day, compared with the cost of our existing hybrid solar generator system in orange. The costs are estimated for a period of 25 years, which corresponds to the lifespan of the solar panels. The results given by this analysis are presented in this table. We have a return on investment of solar system equal to 32 months only. The cost saved with solar system after 5 years are equal to $48,000. After 10 years, $128,000, and after 25 years, they are calculated as $300,000 US. Considering the total volume of water distributed after 25 years, the whole life cost of 1 cubic meter of water is equal to $0.26 US per cubic meter with the existing solar system, while with the generator only, the whole life cost is calculated as $0.31 US per cubic meter. So coming to the end of this presentation, just summarizing the key points that were mentioned. The solar water pumping system has the capacity to provide an average of 500 cubic meters per day, which represents 99% of the water that we distribute. Currently, the generator is used only during the rainy season or for emergency, and it supplies an average of 4 cubic meters per day. The return on investment is only after 32 months, and it's important to minimize the operation and maintenance requirements with clear handover and warranties with the contractors. And finally, most, not all, but most of operation and maintenance tasks are done directly by trained IOM volunteers from the affected population. Thank you very much for your attention. In case of any question, I'm happy to respond. Over to you, Ranisha.
Thank you so much, Alessandro, and also to Alberto. I'll quickly switch back to my screen. And moving forward, as we have some time delays, I would like to quickly invite our last presenter for today, Paige D. Campbell from Sunspire. Paige is currently managing multiple existing solar testing laboratories for Sunspire and is also responsible for the opening of new locations and reporting to the CEO and a part of the company's management team. He also plays a key role in executing the company's business strategy. And today, Paige is going to talk about what are the indicators for selecting good solar panels. Paige, the floor is yours. I'm going to quickly send you a request to share your screen.
Thank you, Ranisha.
Perfect. Now, if you could accept my screen, we can begin with the presentation.
Great. Well, thank you again. And a special thank you to the organizers of this webinar. In addition to the audience, I look very forward to giving some information and some tips on how to monitor and how to validate, but ultimately how to secure module quality in a humanitarian context. Now, Ranisha has already done a very good job of introducing myself. My name is Paige T. Campbell. I'm responsible at Sunspire for our quality control laboratories, in addition to other quality control services that we provide to our customers in Asia and other markets. And I will carry on now to the content of my presentation. A very short introduction of our company, and I will make it even shorter due to time. We have been active in the solar business since, let's say the dawn of solar globally. In 1969, our company was founded in the United States, and we are specialized in the output and overall quality of PV modules. We have become the company that we have today over the last 50 years through the production and sales of very highly technical PV testing equipment, in addition to turnkey production lines to all module manufacturers globally since the beginning of the production of PV modules. In the present day, we are more than just a equipment manufacturer. As I mentioned already, we are also providing downstream quality control services to all global players, including buyers of PV modules and systems who want to validate quality and performance. We do that in two different ways, through checking PV modules during production in the Asian or other country manufacturing facilities with our own inspectors. And we also have physical laboratories in strategic locations where PV modules are imported into specific countries. So we have been around for a very, very long time, but our expertise and our experience is specifically focused around the quality and output of PV modules. And I will go forward to discuss some of the challenges that can come in a humanitarian context regarding the quality of PV modules overall. So there are some key challenges when purchasing a solar-powered water pumping system in a humanitarian context. So in these places where these systems are being installed, there is 5 key challenges that are presented. Know-how and expertise can be a challenge in a humanitarian context if these two are missing. It becomes very difficult to identify a real module versus a counterfeit one, or a module of a high quality versus low quality if those two are missing. The overall module quality itself is very important and very difficult to identify if you don't have the first part. Another very real challenge, which we've seen in the news and also in practice, is the actual authenticity of the components themselves. And this part, of course, does not only relate to PV modules, but also to other key components like inverters. There have been many cases where is the PV module or other components real or not? And I have seen such dramatic examples where a completely fake item has been shipped, where you open the box and it's not really a PV module, but something that looks like one that has no ability to generate power. So this is also becoming an issue as the uptake of solar increases. And in countries where awareness of module quality or authenticity is low, these are the countries where risk is the highest for this problem. So we will discuss that as well. The other challenge is, of course, damage. In the picture you see, transport damage, of course, but there can be other types of damages to PV modules or components during the production, and we will discuss that shortly on in my presentation. When we are transporting PV modules to very remote countries and very remote locations, of course, the quality of the infrastructure and the quality of the transport systems can play a major role here. And this can, of course, dramatically impact the quality of modules as they are received into the remote locations where they will be installed. The last point, of course, is the output of the modules themselves. This can be, of course, a very determining factor in the success of the project. If the modules are unable to power the pumping system, that can, of course, be catastrophic for the success of that project. So, in conclusion, these 5 challenges can severely, negatively impact project lifetime, but also single-handedly determine the success of that project. I will get into some very specific items on how to identify that and what are the issues that are at hand. These ones are specifically related to PV modules, but there is, of course, some overlap with other key components such as inverters. To check authenticity, there are a number of key things that can be inspected visually where that can be validated. On fake or relabeled PV modules, you will see frequently that the orientation of the label on the module itself is not straight. Most module manufacturers are capable of receiving almost 100% straightness of the labels on the modules. However, if these modules are counterfeited or relabeled manually by hand, you will see that the label is not straight. Cell alignment is another one. Cell alignment in relation to the bus bars can be observed visually. The orientation of the junction box can also be inspected. If it's not straight, that can be a sign that it is not from the manufacturer that is on the sticker. Connector branding can also be a telltale sign. If there is no branding whatsoever on the connector or an unrecognizable brand, that can be a sign of a non-authentic component. Glass or plastic, it sounds almost unbelievable, but sometimes with completely non-authentic PV modules, there will not actually be glass in the module, but a very cheap plastic that is just simply designed to look like an authentic unit. The coloration of the cells can also be a very telltale sign. You see in many systems where they are a clear blue. However, if they are not uniform or checkerboard or completely different, this can be a sign of poor authenticity. Packaging, of course, is very important. A very telltale sign of concerns around module authenticity is if the packaging is different or not branded in accordance to the modules or components themselves. For example, if you buy inverters from a well-known inverter manufacturer, but there is no branding on the packaging, that is a very large concern. The same is for PV modules. In addition to function, for a relabeled or non-performing or even fake module, of course, there will be no electrical connectivity in that module, which can be tested, of course, very simply with a multimeter. And there is an IEC standard that goes through what is called visual inspection, which can be used as a guideline to determine authenticity of a PV module. In addition to that, we have also EL testing, and I will show you some examples of that. What is EL testing in a subsequent slide? It is an X-ray for a PV module that can identify micro cracks, soldering defects, delamination, grid finger defects, and all kinds of other various physical problems with PV modules that can impact functionality or performance over time. We will get more into detail in that shortly. Then we have performance. Of course, module function. If the module does not function at all, there will be no success with the project, and also significantly lower Pmax than what is advertised on the sticker or in the data sheet. So there is, of course, for that. IV testing. IV testing is one of our specific expertises. We have been manufacturing equipment for that for decades. However, there is, of course, affordable and accessible equipment to give access to tracing an IV curve in the field, and I will show a couple of examples of these tools here now. The point that I am trying to make with this part of the slide is, well, in the humanitarian context, for example, if we are doing a solar project in Bangladesh, as presented by my previous colleague presenter, there are very affordable tools that can be accessed to validate quality even in exceptionally remote areas. And these tools are readily available and also affordable and easy to use. A handheld IV tracer can, within seconds, validate that the module is functioning, but also can say something about the performance of that PV module in relation to what is expected from Pmax. We have also on the market for multiple manufacturers portable EL cameras. And just to introduce the audience to what is EL, well, that means electroluminescence. And it is a phenomenon that was discovered almost 100 years ago, where when a current is applied to a particular compound or even a electrical component, that light is emitted from that, which enables a infrared photo to be captured. And in the photo on the left, you see a very simple setup with a EL camera powered by a battery that takes a picture of a solar panel that has a current applied to it. And in this case, current is always equal to ISC. that current can be applied in a very simple method through a power supply connected to a generator, where you can validate any type of physical damage to that PV module. And with these two very easy to use and affordable devices, you can really identify quality issues even in the most remote parts of the world. I wanted to also share a little bit of visualization of quality issues. Of course, it doesn't end at the modules themselves. We see many issues and are asked many times to inspect modules that have been already installed. The installer, of course, plays a major role in the integrity of the module. If that module is poorly handled or damaged during install, that can, of course, be a major issue. And that quality of the install can be validated by those two devices that I have put on the screen in my previous slide. Transportation damage is very obvious, but this is really, a very critical thing to look at when you are purchasing modules or are receiving them on site. The transportation, can be a very big problem in relation to damage. If the packaging is damaged or torn apart or slanted or is obviously been rough handled, that is a major problem and should be identified and handled accordingly. The big advice here is if the product is arriving to the site and looks poorly handled, there may be a case to not accept that before you become the owner of the product. You see here on the right-hand side as well, it might be a bit difficult to see on my screen, but in this specific installation, there is a clear noticeable difference in the color of the cells. So the colors of the cells are not uniform. Some are blue, some are black, some are light blue, some are dark blue, and this is a very telltale sign of poor cell quality and mismatched cells. That is not something that you would normally be able to see with the naked eye. If you are standing 1 meter in front of a solar panel, the color of those solar cells should be the same. And that is a tip that I will offer to the audience to be able to validate general quality of the module itself. The key message to this particular slide is somebody needs to be able to identify quality issues. If you are going to do a solar project, whether for water pumping or otherwise, there just simply needs to be at least somebody that can identify these types of issues and be able to take action upon them. And training one person on the very basics of PV quality is relatively simple, and the training does not need to take days or weeks. A very simple overview of what to look for is all that you need. A few more examples here. I've talked about EL already. This is on the left-hand side is an example of a EL module that has been taken with our portable EL camera. To the naked eye, it looks totally normal, but in reality, it has been poorly handled. Somebody has dropped this pallet, and you can see the catastrophic damage to the module, not by the naked eye, but only through an electroluminescence camera. And that is a really great tool to have to be able to identify these types of issues. Another one that you can look for is the barcodes. Most manufacturers have a numbering system that lines up to the manufacturer. If that numbering system does not line up to the manufacturer on the sticker, that is almost guaranteed case of non-authenticity or relabeling. Furthermore, performance visualized on the right-hand side. This is a little snapshot of our test report where we have measured a number of PV modules for output. Pmax was measured, and we found that almost all of the modules in this test sample was completely less than the nominal value that was advertised. And that data can come out of your handheld IV scanner that I have shared on the previous slides. Now that I've shared a few key challenges, visualized those challenges, this is the part that I think our audience can get the most out of. I'm going to share 2 slides with some key tips on what you can implement right now with your upcoming projects. There are a number of challenges, of course, with buying modules in the secondhand market. Of course, for these smaller projects, buying direct from the manufacturer is not always possible. However, for larger organizations who are doing multiple projects that are centralized their buying efforts, that is possible. But the big tip here is to buy from a reputable wholesaler that is potentially in a different country. So if you're installing a humanitarian water pumping project in a country that is well known for corruption, you may want to consider buying the modules in a country that has less risk of these types of issues, and then shipping them in. That is a tip that you can implement today to eliminate risks of counterfeiting and relabeling and quality in general. Furthermore, defining quality requirements in the purchase contract. And I know that not all module systems will have a purchase contract, but at the minimum, you can discuss what level of quality that you expect from the company that you're buying the modules from. What do you expect for damages, and what do you expect for performance? When you do this, even as simply in a telephone call or an email, you give the impression to the seller that you are somebody that understands quality, and therefore he may be, or that company may be less, there's less risk that modules will come to you completely of a poor quality. Number 3, you can validate quality and performance by testing. And I would highly recommend that you do this before you become the owner of the product. Of course, for modules going to be installed in remote countries, that becomes more difficult, but somebody, of course, can go to the company where you're buying the modules from and inspect them in the warehouse. You can inspect the packaging, you can inspect the quality by doing some on-site EL tests with the equipment that I shared earlier. And you should be able to go to that supplier location to look at the product before you buy it. That is a very big tip that you can implement today to dramatically improve the level of quality of the product that you will receive. If there is something very obvious wrong with that product, you can see it before you agree to purchase it. Last point, which I've already shared, appoint at least one person that can do that. So somebody at the minimum should have the basic knowledge to be able to identify packaging that does not match up with the stickers on the modules, and so on and so forth. We understand that availability of true professionals of quality control in developing countries are very limited, but equipping somebody with the basic knowledge of that will get you miles ahead. Now that I've shared 4 key points, I want to share 4 key tactics. When you are going to buy PV modules or other components, you can ask for data from the manufacturer of those components. So let's say that you are buying modules from a well-known manufacturer. You can ask your supplier of those modules, let's say that it's a wholesaler, for the barcodes and the flash data of those modules that you're going to buy. You can then send that to the manufacturer and ask them to validate that these barcodes are real based on their manufacturing data. You can also ask them for the electroluminescence photos that were taken during production. So every module that is produced globally will have an electroluminescence photo of it taken in the production facility, and this data can be requested from the manufacturer. In my experience, is that they are willing to provide it, especially for these humanitarian projects. Most manufacturers would be more than willing to supply that data upon request. Also recommending that you will inform your supplier that you will check. When you tell a company that there is going to be a check of quality and authenticity, you are already seen as somebody that has far more knowledge than the rest of the market. That supplier is put on high alert, and they will be highly incentivized to send you a product that is of high quality, or they may be no longer willing to sell to you at all for the fear that they will be discovered of their actions. When you do that type of validation, as I mentioned already, you can do it before you become the owner of that product in the warehouse, or at least before you become the owner. That is a major tactic that can be used. And the last tactic is, where possible, negotiate full payment only after you have inspected the product. In this case, you will tie the payment of the product to quality. This tactic is absolutely free. I can imagine that some companies would be not willing to agree to that term. However, there are many companies offering PV modules and systems. Buy from somebody who would be willing to agree to that, which gives you confidence that that company is reputable and can supply a product of quality. The success of these projects and mitigating the risks of authenticity or poor quality requires a bit of out-of-the-box thinking. And I hope that in these last slides, I have provided a little bit of tips and tricks on how this can be done even in remote areas. And I would like to finish my presentation by saying again, thank you to the organizers and to the audience for listening. I've left here my contact information should you seek to reach out to me even after the Q&A of this webinar, which should follow. I'm more than happy to guide you or to answer questions that can help you along your way. Thank you very much.
Thank you so much, Paige. So let me switch back to my screen first. So first of all, thank you for highlighting all those tips. I'm pretty sure our audience are taking notes, and they are really helpful for our audience. And to our audience, we will share the presentation, so you can also have a deeper look after this webinar. And now we move to the Q&A part. We have been receiving a lot of questions. So without further ado, I would like to quickly jump on the Q&A part. And the first question is for Professor Salvador. So Professor, you talked about different types of losses. So from your experience of working in the from directly on the ground, what are the top losses that you see that you encounter the most when you are on the ground, especially in humanitarian relief sector?
I think that the most important part of the losses are related to the temperature. The other factor that can also be important in some locations, like just in Africa or Asia, is that the tolerance of the modules. The quality of the modules is very important, because the losses related to bad quality modules can be very important.
Thank you so much. And there our audience can definitely take the tips that Paige just told about to select a good module. And coming back to one more follow-up question to that, Professor, you talked about the individual losses from individual factors. Is there a cumulative loss percentage or a factor that someone who is doing a back of the hand calculation can take into account for all of the losses on average? Professor, I think you're muted.
Sorry, can you repeat the question?
Oh yes, so you talked about individual loss from, let's say, wiring, dusting. Is there like a cumulative loss that we can take into account that accounts for all of these different factors?
Yes, the performance ratio, this factor is the sum of all the factors, really is the product of the different factors. So the performance ratio is the factor that gives us the idea of how efficient is going to operate our PV system.
Thank you so much. And that you can check out in the presentation that he shared today. And now moving to Alberto. Alberto, you talked about water for payment scheme, not scheme, but payment mechanism. Do you have any example where it has been implemented that you could share with us?
I have to look for those, but yeah, I might have some. I might have some document that is useful for you. Having said that, I will say that is in this attempt to let's say map systems and how they are working, to find assessment and evaluation related on solar projects, they are so rare to find. Yeah, there are so few, and I think that's one of the gaps that if we could, perform a few more, we could have a much better understanding on these issues. But I think I have some document. I will make it available to you, Ranisa, and then you can share it with the audience.
Definitely, we will share it in a follow-up email. So this also shout out to the audience, Hugh. If you also have a case study that Alberto just mentioned about, there is lack of case studies to highlight these things. So if you have something that you want to share with us, you can share it with us, and that can be shared with a wider audience in a follow-up email. So thank you so much. Moving forward, I have a question for you, Alessandro. You showed us cost calculation for this, where you compared the solar hybrid with diesel. Did you also include the end of life management costs into this calculation?
I think that one was included as well. I can check better with Alberto. He was supporting this this analysis. Alberto, you may correct me if I'm wrong, or confirm me that this is there.
No, I need to check the numbers to see if it's there or not. I'm not sure. But I can recall other studies where we took those costs and they have like a minimal impact on the conclusions of the economic analysis in terms of break-even point or cost save is very minimal. But I'll check that.
Thank you so much. And there, I should also like to highlight that in one of our previous webinar, we also, like Alberto mentioned, we also presented the LCV for other projects, and there we also linked up the tools, the instructions, and other information. So if you are interested in having access to that also, you can check out the link that my colleague dropped earlier in the chat box, and you can have access to all those materials, including the Excel sheet that both of our presenters showed today. Thank you so much. And Alessandro, one more follow-up question to you is, what was the average age of the facilities that were surveyed?
So the average, sorry, I didn't get.
So the average age of the different facilities that were surveyed in your case study in Bangladesh.
The average age of the facilities.
In terms of how many, so how long has it been since they were installed?
Okay, the water supply system that was presented was installed in July 2019.
Okay, so almost a year or more than a year.
It will be 2 years, 2 years soon, in a couple of months. And till now, no major issues. I mean, me being the head of the unit, I will have an immediate understanding of any major issues, because I would be the one signing procurement papers to purchase anything that is needed to fix any issue. And after almost 2 years, these never occurred. So we never face any major issue.
Thank you so much. Now, Paige, I'm moving to you. So there is a question. It's a very long one, so I'm going to read it directly to you, Paige. So we are facing the challenge that there are a lot of cheaper and lower quality solar power pumping system products which are imported in Sudan market or African market in general, and these products are spoiling the SPWP reputation. What can we do to resolve this situation?
My main advice would be to revert to some of the tricks that I have provided. And in the first tip on my first slide was to buy the products potentially in a different market. So if you are buying these components in markets where you are seeing a very high level of counterfeit or low quality components, also consider buying those from a country that has less risk of these products. You can, of course, purchase these products even outside of the African continent, and arrange for them to be shipped in. And I would even welcome this person with this question to write to me directly, where I can connect you with some companies, even in Spain, that would be willing to ship the products to you in Sudan. The second answer that I would give would be also relating to the tips and tricks that I gave. You need to be able to validate that quality. So even if you want to, even if you are considering to purchase a system that is, relatively cheap, you still have the opportunity to validate that quality before you buy it. You can send somebody to the location of your supplier to look at the packaging, to even turn on the product and test it before you buy it. And I know that sounds like a lot of extra work and cost, but look at the impact of these solar projects. Okay? My belief is that the impact that these projects are making deserve extra steps and extra inspection to mitigate the risks of authenticity or poor quality in general. And if I can provide any further or additional answers to this question, please feel free to reach out to me directly.
Thank you so much, Paige. And to our attendee who asked that question, please reach out to him directly, as he shared his contact information in his presentation. And that brings us towards the end of the webinar. I know we have a lot of other questions that we have not tackled them as of in this webinar. So we will tackle them after this webinar and upload them as written answers so that you can read them later. And also a quick note that we had a lot of questions about retrofitting. We already tackled that topic in our second webinar, so please have a look at that. We had some about tank sizing that was tackled in either both second and third webinar, so please also have a look at that. And that brings us towards the end of the webinar. First of all, a huge thank you to our presenters for all of your amazing and insightful presentations. A huge thank you to our attendee for staying with us towards the end. And as you can see, there are a few links, further information links, which you can access, including the publication that Professor talked in his first presentation. And yes, we will share the recording and presentations with you after this webinar. And one more time, thank you so much. And please fill out the survey that will go out after this webinar. Your answers will help us to design the upcoming webinars to meet your needs. And thank you and have a good day and bye-bye.